In this lecture, we are assuming that if you are watching this lecture, you have at least attempted the counting project that was assigned to you in the previous lecture. The counting project asked you to take 25 to 30 toothpicks and count them using numbers or symbols of your own and not your normal base 10 system, decimal system that you're used to counting in. The experience of creating this amongst different students and groups probably shared some similarities. The similarities probably included some sort of grouping or bundling. You had to discuss what one object represented for you, what symbol you used for it, then what two objects meant. Some of you used tally marks, some of you used letters representing numbers, and so on. The smallest number of objects in your bundle, that will determine how you're going to count the rest of the objects. This smallest number is referred to as the base of that number system. So our decimal number system is base 10. We must be able to extend our system to larger quantities of objects, which some of you may not have had. In fact, some of you had difficulties extending your counting system to larger numbers because you ran out of symbols possibly. Our system must be also consistent no matter who is interpreting that system. So there are a few things you had to keep track of when you were doing this counting project. Perhaps you used symbols and ran out of the symbols when encountering large numbers, but suppose you had enough symbols to represent large numbers. How do you combine one or more symbols together to create a third symbol? And that should represent also the collection of objects that you entered. So counting project was not that easy. And there are also other issues like doing arithmetic and not just counting, but doing other things with them. And so we wanted you to experience what was involved in determining your own number system and how you would extend it to larger groups of people or numbers. So number systems, even from primitive humans to the most advanced civilizations, all felt a need to develop number systems and standard units to make objective sense of the world around them, from bartering for food or clothing, or keeping track of the possessions like sheep, to science like biology, physics, chemistry, astronomy, and technology. Numbers help us facilitate quantitative communication, which means communication involving quantities or numbers. The oldest form of numeration was by use of tally marks in the Stone Age, approximately 25 to 35,000 years ago. People know this from artifact bones found that had these tally marks on them. The way it works is you write 1, 2, 3, 4. The 4 is represented by 4 vertical tick marks, and 5, the fifth horizontal tick mark, represents bundle of 5. To this day, we use this tally mark system to count simple things. As human societies got more complicated, tally system became cumbersome, which prompted the development of many different number systems. You can look at history of mathematics books as well as the internet as a resource if you're interested in history of numbers. Past civilizations like the Babylonians used base 60 number system around 3000 to 2000 BC. For example, in their number system, 12,074 number would be represented in the following manner. The upside down triangle represents 1. The sideways symbol represents a group of 10. So this is 14 groups of units, 21 groups of 60, and 3 groups of 60 square or 3600. The Mayan, as the Aztecs, wrote the numbers up and down as opposed to sideways, and they used base 20 system around the 4th century AD. All three of these old civilizations did very complex astronomical computations using their number systems. So to understand our decimal number system, we have to know that we're looking at base 10 and groupings of 10. Our decimal number system is sometimes referred to as the Hindu-Arabic system, and Bhaskaracharya has been credited to cataloging this system, the base 10 system. invention of zero, which was referred to then as shunya, means nothingness, seems easy now, but at that time was very controversial and took a long time to gain acceptance. So let's review the basic decimal number system counting, because understanding the decimal number system will allow you to understand other mathematical objects like polynomials. So 0, as we talked about, represents no objects or nothingness. And we start then with a single object, 2 objects, 3 objects, 4 objects, and all the way to 9. When you add additional object to 9 objects, you'll end up with 10, which we write as 1, 0, 0 singles and 1 group of tens. If we add another one to this, you'll end up with 11, which would be 1 group of single and 1 group of 10. So we have 1 bundle of 10 and 1 singleton left. Then we have 2 singletons and 1 group of 10, which represents 12, and then 13, 14, 15, and so on. We go all the way to 99, and when you add another object to this collection, you'll end up with 0 singles, 0 groups of tens, and 1 group of 10 tens, which is 100. And that's how you move in your decimal number system. So for example, 324 would be 4 groups of singletons, 2 groups of tens, 3 groups of 10 tens, or 100s. We can also represent numbers in this decimal number system smaller than 1 as fractions out of powers of 10. So we can use the decimal point, which identifies the end of the whole number and beginning of the fractional part. So for example, 3/10 is represented as 0.3. The 0 is telling you you have 0 units placed, and the numbers that come after the point are fractional parts out of powers of 10. The first number represents 3 parts out of 10, or 3/10. The number 324 over 100 represents 3 singles, 2 tenths, and 4 100ths. So multiplying and dividing by powers of 10 becomes easy in our decimal number system. So we can have 324 multiplied by powers of 10. We'll end up with 324,000. That simply means 32,400. The decimal point is not, when not written, it's assumed that it is on the rightmost endpoint here. If I write the number 3.24, then that would be, I would have to divide 324 by 100 like you saw here. So dividing by 100 or multiplying by 100 simply makes the decimal point move. So to understand our decimal system, this chart will help you. We use decimal point to separate anything higher than 1 with smaller fractions like a tenth and a hundredth. We know that when you go from smaller place to larger place value, like hundredths to tens or ones to tens, you need 10 of the lower one to get a higher one. So 10 100ths will make 1 tenth. 10 1/10ths will make 1 ones. 10 ones will make 1 group of tens. 10 tens will make 1 group of 100ths. Similarly, if you're going from hundredths to a tenths, you go division by 10. If I have 100 divided by 10, I'll end up with 10. 10 divided by 10 will give me 1. 1 divided by 10 will give me tenths. So what that means is that in the decimal number system, we're choosing to bundle in groups of tens. So the number 324 can be written in this format, and replacing different components in here will give us different objects. This is what playing in mathematics means. So let's take a look at what that really means specifically. For example, if we look at the number 324, replace all the tens with x's, we end up with this object. So we replaced all the 10s that you see here. 10 squared is now replaced with x squared. 10 to the 1 is now x to the 1. 10 to the 0 is now x to the 0. This object, this new object, is called a polynomial in x. If you do the same thing with all decimal numbers, that is, replace all powers, the base 10s with x's in decimal numbers, you create an object called algebraic expression. So for example, a 10th, which is 1 over 10, will be replaced with 1 over x, and so on. So a polynomial is a special case of algebraic expression. We'll work with this more in depth a little bit later.